Hey there everyone, welcome back to our investigation in Unit 5, Analytical Applications of Differentiation. Today we're going to talk about using the candidate test to determine absolute or global extrema. Okay, so we talked before about extrema and relative versus global, or local versus absolute, or however you want to say it. This is going to help us find absolute minima and maxima on a closed interval. Okay. To find extrema of a continuous function f on a closed interval a to b, we use the following steps. First thing, as we've been doing a lot recently, is we find the critical numbers of f on the open interval. We evaluate the value of f at each critical number, and we evaluate the value of f at the endpoint. The least of these f values is the absolute minimum, and the greatest is the absolute maximum. All right, but the key here, we talked about before when we talked about extrema itself, is that the function must be continuous on the closed interval. Okay, if it's not, then we cannot use the candidates test. Okay? So, important note down here, if a question asks you for the actual maximum or minimum value, then it's asking for the y value. But if it says, where does the function reach a maximum or minimum value, that would be asking for the x value. Okay? So let's jump right in and take a look at an example here. Find the absolute extrema of f of x on the closed interval -1 to 2. Your first thought is this function continuous on this interval? And this is just a quartic function which is continuous everywhere. So if it's continuous everywhere, then yes, it's continuous on this interval. So we're now going to take the derivative and see where the derivative is either 0 or undefined. Okay? This is a cubic function. This will never be undefined, but it will be 0. And if we factor out the GCF of 12x squared, that will leave us with x minus 1. So x is either 0 or x is 1 are our two critical numbers. Okay? So then our candidates for this here are going to be the two endpoints, and the two critical numbers. So those are our candidates for absolute minimum or absolute maximum on this closed interval. Okay? So at this point, all we're going to do is make a little table, a little x versus f of x table. And if you want to make a vertical table or a horizontal table, whatever is fine. And I'm going to write down all my candidates here in numerical order. Doesn't really matter. I mean, no one's grading your table. It's like no one grades your sign charts, but it's nice to keep things organized. And we're going to find the y values of each of those, okay? So the y values, remember to get the y values, you're simply going to substitute those numbers back into here, okay? So if you put -1 in, we would get 3 times 1 minus 4 times -1, which is 3 plus 4, or 7. If you put 0 in, you get 0 back. If you put 1 in, you get 3 minus 4, which is -1. If you put 2 in, we will get 3 times 16 minus 4 times 8, which is 48 minus 32, or 16. Okay? So the candidates test says, on this interval, the absolute max and min must come from one of these 4 points. It can't come from any other points besides those 4, because those are our endpoints and our critical points. So our maximum is right here, and our minimum is right here. Okay? So the question says to find the absolute maximum and the absolute minimum. Okay, so the absolute maximum of 16 at x equals 2, and the absolute minimum of negative 1, and that occurs at x equals 1. Okay? Quick note here on this. Two mistakes that I've seen in my years of experience here. For a problem like this, we're not choosing these four numbers just because they're all the whole numbers between negative 1 and 2. That's something I see a lot, okay? You don't just use all the whole numbers, okay? Sometimes we have critical points that are not whole numbers, or endpoints that are not whole numbers, and that's okay too. Sometimes we don't use all the whole numbers. The only reason why we're using these four numbers is we're using these two because they're endpoints, and we're using these two because they're critical points. That's the reason why we're using these numbers in our table. Okay? So let's try another one. Find the extrema. So we already have two candidates, negative 1 and 3. Let's see if we can find any more candidates. F prime of x equals 2 minus 3 times 2/3, which is 2x to the negative 1/3. And if we rewrote that, it would be 2 minus 2 over x to the 1/3. Okay? So first of all, we can see there's definitely at least going to be one other candidate. When x is equal to 0, this is going to be undefined. So we just found a third candidate for our test. Now we have negative 1, 0, and 3. But now we need to also see if our derivative would ever be equal to 0. So solving this, we get another candidate of x is equal to 1. So we have four candidates. Negative 1 and 3, 0 because it's undefined there, the derivative is undefined there, and 1 because the derivative is 0 there. So we have four candidates for our table. Okay, and again, we'll list those in numeric order. So negative 1, 0, 1, and 3. Notice how I didn't include 2, because again, we're not just picking all the whole numbers like I've seen a lot of students do in the past. Okay, we're picking these four numbers because they're either endpoints or critical points of the derivative. Critical points of the original function from the derivative. All right, now we simply get our y values back. So if we put negative 1 in, we would get negative 2 minus 3 times negative 1 to the 2/3. Okay, so that's negative 2 minus 3, which is negative 5. 0 is always nice and easy, so 0 minus 0, that would give us 0. 1 gives you 2 minus 3, or negative 1. And then 3 gives us 6 minus 3 times x to the 2/3. So 6 minus 3 times 3 to the 2/3. Okay? 3 to the 2/3, so if we simplify that, that would be 6 minus 3 times, 3 squared would be 9, so that would be the third root of 9. All right? So a quick note here on what this would approximately be. The third root of 9 is a little bit bigger than 2, okay, because the third root of 8 would be 2. So the third root of 9 is a little bit bigger than 2. So 3 times that would be a little bit bigger than 6. So 6 minus that number, this number is just going to be a little bit less than 0. Okay, so maybe we could just say slightly less than 0, just barely. Okay. We don't need to know its actual value, because good news, it's not one of our answers. Okay? The biggest number on this interval would be 0. It's bigger than all these other three numbers. The smallest number on our interval would be negative 5, because it's smaller than these three numbers. So now we can write out what we know. On this interval, we have an absolute maximum of 0, and that occurs at x equals 0, and an absolute minimum of negative 5, and that occurs at x equals negative 1. All right, question 3. So find the extrema of this function. Here we already have 2 candidates, 0 and 2 pi, because those are our endpoints. Let's see if there's any more candidates. By taking our derivative, which would be 2 cosine x minus sine 2x, minus negative sine 2x times 2. So that'd be plus 2 sine 2x. Okay? That'll never be undefined because cosine and sine are always defined. So we're good there. Okay? And to get the other part where this would be 0, we got some work to do here. 2 cosine x plus 2 sine 2x. In order to make this a lot easier on ourselves, we should use an identity we learned last year in our pre-calculus course. Sine 2x is the same thing as writing 2 sine x cosine x. That's going to make this a whole lot easier to solve. So now if we do a little bit of simplifying, and then I factor out a GCF, I either get 2 cosine x equals 0, or I get 1 plus 2 sine x equals 0. So this is going to be when cosine x equals 0, and that's going to happen at pi over 2 and 3 pi over 2 on our interval. Or this is going to be when sine x equals negative 1/2. Subtract 1 and divide by 2. Okay, and sine x equals negative 1/2. That's 7 pi over 6 and 11 pi over 6 on our interval, which means we have 6 candidates. That's a lot of candidates here. All right, so let's make a table. X f of x. Okay, in numeric order. So we have 0 and 2 pi at our lowest and highest points here, and all the points in between. So that would be pi over 2, seven pi over 6, 3 pi over 2, and 11 pi over 6. All right, so we just got to take those numbers and put them into the original f of x and get back our values here. So hopefully you know your unit circle. We would have, when x is 0, we would get negative 1, and then so forth and so on. So pi over 2, 3, 7 pi over 6 would be negative 3 over 2, 3 pi over 2 would be negative 1, 11 pi over 6 would also be negative 3 over 2, and then 2 pi would be negative 1. So the highest value is 3, and that occurs here. The lowest value is negative 3/2, and that occurs more than once. And that's okay. Absolute extrema can occur more than once as long as it's the same y value. All right, so let's write out our answers here. We have an absolute maximum of 3, and that occurs at x equals pi over 2. And we have an absolute minimum of negative 3/2, and that occurs twice at x equals 7 pi over 6 and 11 pi over 6. Okay, and if you want to see graphs of those three, you can see what those look like here, and you can see the first one, absolute maximum, absolute minimum. The second one, absolute minimum, absolute maximum. And the third one, absolute maximum, and then 2 absolute minimums right there. So this is also applicable to our velocity, position, velocity, and acceleration problems that we were working on last chapter. Okay? So a particle moves along a straight line with position given by S of t between t is between 0 and 3. Find the minimum and maximum velocity of the particle on the interval 0 to 3. Okay, so the first thing we need to do is find the velocity. So v of t would equal 4t cubed minus 12t squared plus 12t plus 0. And now we want to know the critical numbers of velocity. So we want to know when the derivative is either 0 or undefined. It'll never be undefined, but it will be 0 when t equals 1. So that gives us 3 candidates, 0 and 3, and 1. So we make our candidate table here. 0, 1, and 3. And we put those in the velocity at 0 is 0. The velocity at 1 would be 4 minus 12 plus 12, or 4. And the velocity of 3, if they're putting 3 into the velocity function, you would get back 36. Pretty obvious here. Minimum value, maximum value. So those are our answers. Okay? So the particle would have a maximum velocity of 36. And that would occur at t equals 3, and a minimum velocity of 0, and that would occur at t equals 0. Now question B just says, all right, well, what's the minimum and maximum acceleration? Well, in order to do that, we would need the acceleration function, which we already found in the last problem. Let's just copy that down. Remember, acceleration is just the derivative of velocity. So we want to find the critical points of acceleration. That means we need the derivative of acceleration, which is 24t minus 24. We want to know when that would be 0 or undefined. It will never be undefined, but it will be 0 when t equals 1. So it's actually the same 3 candidates that we had in the last one. So let's make our same chart that we made in the last one. T, but this time we're talking about a of t. And we got 0, 1, and 3. Placing those numbers into acceleration, the acceleration at 0 would be 12. Acceleration at 1 would be 12 minus 24 plus 12, or 0. And acceleration at 3, if you plug 3 into t there, you would get 48. So you'd have a maximum acceleration of 48 at t equals 3, and a minimum acceleration of 0 at t equals 1 on this closed interval 0 to 3. All right, that will do it for our look into the candidate test for absolute extrema. Thanks again for checking out my video this time, and we'll see you next time.